So everyone likes setting up VLANs on their home network. But can you tell me the difference between a layer 2 VLAN and a layer 3 subnet? How do you choose the numbers for your layer 3 subnets or your layer 2 VLANs? Today we're talking all about arranging our network into subnets, how we can do that, how we do that in IPv4 and IPv6, the current version of the Internet Protocol, and how we can use VLANs or virtual LANs on layer 2 to help reduce our wiring clutter. These two technologies aren't the same, but they're often interchanged, and that's why I think it's important to talk about them. In this video, I'll be using my favorite open source firewall, OPNsense, to demonstrate how to implement the concepts. But of course, you can take this back to your favorite firewall of choice. So come along with me on this adventure. This video is brought to you by Tronsmart and their T7 portable wireless speaker. You might not know this about me, but all of my favorite music happens to be in the YouTube audio library, where I can listen to great tracks without worrying about copyright strikes. And when I'm in the studio, I need a great speaker for all that free audio. The Tronsmart T7 is a Bluetooth speaker that I can use to do just that. I can pair it with my phone or laptop, or even an SD card, and get on with the studio jams. The LED volume knob also has a very satisfying feel. It's also IPv6 waterproof in case you drop it in the hot tub or your cat's sink. The hanging strap might be useful if you bike, but I'm American, so I don't own a bike. It has an 18-meter Bluetooth range, which is 58.5 freedom units. If you happen to find yourself too far from your gamer shed, you can also play tunes from the microSD card, no phone required. It's got some pretty kickin' bass for your late night raves, and a 12-hour battery life so you can go all night long. And finally, by the magic of getting two of them, you can pair them together for stereo sound. Find yours at the link in the description. Now back to the video. So starting from the last video, we had a very basic setup. We had the internet coming in on a green cable, and we had the LAN going out to just my laptop on a black and yellow cable. So firewall router's chilling. It has these subnets it gets from the ISP, so this is our delegated IPv6, and this is our CGNAT IPv4. We then create two subnets on our LAN network, so that's our IPv6 subnet, that's our IPv4 subnet, and our computer gets two addresses, one via Slack for IPv6, and one via DHCP for IPv4. So let's start by brushing up on what a subnet really is. You've probably seen a subnet written in what's called CIDR or CIDR notation. This is something like 192.168.1.1/24. That /24 is the number of bits which are part of the prefix of the subnet. So in IPv4, addresses are 32 bits long and they're represented as 4 8-bit octets. So if we have a /24, that means we have 3 8-bit octets that are part of the prefix, and 1, the remaining, 32 minus 24, is 8. 8 bits are left over. Those become the host section. So in this guy here, 10.212.46.10, the first three, so 10, 212, and 46.0 would be our network, or our prefix, and then 10 would be our host. And it works exactly the same way in IPv6, except our addresses are longer, 128 bits. So thankfully for us, subnets are almost always 64 bits if they're for devices. So in this example, we get to split the address directly in half. 64 bits for the prefix, 64 bits for the host. So 2001 DB8 6969 FEV1, that's our prefix. And then 512B D36F D069 519A, that's our host. So next up, I have a pretty simple scenario where I've connected my laptop and my desktop to a dumb network switch on my LAN. So just to shorten things up a bit, I'm using 2001 DB8 as my prefix and just 1, 7, and F as my host addresses. So all three of these are on the same subnet. This has access to the internet, which is everything else. So what happens when my laptop wants to send a packet to my desktop? How does it figure out where to go? So the first thing it does is it wants to send to 2001 DB8 F. So now it needs to decide what of its own source addresses it should use. Remember in IPv6, we can have as many source addresses as we want because we can be on a bunch of subnets at the same time. Perfectly valid. So in this case, it says I also have an address on that same prefix, and that is 2001 DB8 7. So I'm going to use the address that most closely matches my destination. Now, it can say, since these two are both in the same prefix, I go directly on link. So an IPv4 would have been an ARP request. In IPv6, it's NDP, Neighbor Discovery Protocol. But it's going to try to find the MAC address of the host directly on link. And then it's going to send the packet up to the switch and send it back over here. So now what happens when my host wants to go anywhere else, even if it's a nearby subnet within my home? So what happens if I want to go to 2001 DB9A? So that's not part of my same subnet. The prefix is different. So I need to find a router that can route me to this prefix. Just like in IPv4, if we can't get there on link, we'll go to the default route, which in this case would be our OPNsense router. So we're going to initially say it needs to go to, so it needs to go from 2001 DB8.7, and we're going to do an ARP or neighbor discovery request to the router, which is our default router. We're going to send the packet there, and then routing the packet is going to become the router's problem. The router has to decide where 2001 DB9 is so it can send it there. So that's the big difference between layer 2 and layer 3 networking. In layer 2, everything is based on the MAC address. So when we want to send a packet, we have a source and a destination MAC. That's the physical Ethernet cabling. So when we start getting into IP addresses, which most software relies on IP addresses, not MACs, we need to translate those into MAC addresses. If they're not on the same subnet, it's going to go straight to the default gateway. So if you try to have a server and a client on two different subnets, they're both going to send their packets to their respective default gateways and hope that the gateway can route to the correct destination. So in general, when clients speak directly to each other on the same subnet, it's very efficient. They're going through the number of switches that it takes to get there. They're taking the most direct path. However, this means that we're relying on our individual clients to firewall themselves. Some clients are very good at this, but others not so much. So here in this example, I have added a security camera to the mix, and it has no security to speak of. So let's see what we can do to secure it a bit. So we don't want anyone to be able to talk to this camera unless we've authorized it. So we put it on a second subnet, and that means that now when these clients want to talk to the security camera, they go to their default route, which is our firewall router. Our firewall router now can have rules in place to decide where to send packets and what to allow. It can choose to allow packets to this destination or to this subnet as it chooses, as we've configured. So this is one of the main reasons you'll use multiple subnets in your network for security segmentation. By creating more than one subnet, you isolate who can talk to who and enforce that those connections must go through your firewall router. This isn't the only way to do security, of course, but it's certainly the most common right now. Now, other reasons to segment your network include having multiple physical locations. In general, having a single subnet span multiple physical locations is a bit of a challenge, so using routed networks in that case makes a lot of sense as well. Down here in the lab, I got my OPNsense box from last time, and we're going to try to recreate that setup. I've got a Ethernet camera, and I've even got a pink Ethernet cable to match the colors from my diagram. So my first port is LAN, my second port's WAN, so the third port, so now we're in OPNsense. Now we've got to add that interface and give it an address. Just going to name it interface, so we have LAN and we have WAN, so we need to make a new one, assignments. So we can create a new interface, so IGC 2 and 3 are the ones that are unused. So 0, 1, 2, 3, those are the ports on the physical device. In this case, I'm going to use 2 because it's the third port, 0, 1, 2. We're going to call this cameras. Click. So that's good. We'll save that. So cameras are now created. Come over here to cameras. We can enable it, and then we can give it some addresses. So like in the last video, we have to come up with an IPv4 and IPv6 subnet for our new interface. But we can't use the numbers we used last time. So last time I used 10.212.46, so today we use 47. So static, and we can come down here, 10.212.47.1, and it'll make you a 24 as well. And then for IPv6, it's even easier. We can use the delegated prefix like we used last time. Last time we used number 1, this time we use number 2. So track interface, and we come down here, we're going to track the WAN interface, and we're going to use prefix ID 2. So just a reminder, the prefix we get on our WAN interface is some larger subnet, and we're splitting it down to smaller /64s. And so this prefix ID is what number we add to get that, is essentially like the middle part of the address. So we've got a /62 or a 60 or whatever from our ISP. We have a 64, that's the host part of the subnet on the end. There's 2 little bits in the middle that we need. And that's what we're filling in here, these 2 bits. And again, allow manual adjustment because we're going to want to set that up. So let's save that and apply changes. So because we set this interface up manually, we have to go through all the steps of configuring it that the wizard did for us on LAN. So that means setting up all the router advertisements, DHCP, anything else. None of that's going to be set up. So let's set up DHCP and router advertisements now for this new subnet. So I'm going to enable DHCP, and we can give it a range. So the valid range here is from 1 to 254. So we'll say, I don't know, from .10 to 254. Seem reasonable? That'll leave us 9 addresses left if we want to allocate anything statically. Probably won't allocate anything statically, but whatever. Don't have a lot of space in v4 to waste anything. And we'll let everything else get populated automatically and save that. And then down here in RAs, router advertisements, we're going to set these to unmanaged again. So unmanaged uses Slack, if you recall, so we're going to use that. And again, we're going to let these two be auto-populated. So we're going to use DNS configure from DHCP. Even if we don't use DHCP v6, it'll still pull the DNS configuration from there. And if we don't configure it there, it'll automatically get pulled from the system, which we want. So now let's see if we found our camera and it got an address. So let's look at leases. Looks like something got a camera. That sure looks like a camera to me. And it got .10, so let's see if we can go there. Just a friendly reminder, traffic from LAN to any is allowed by default. So because my laptop's on LAN, I didn't have to create any firewall rules yet, but I'm going to have to. Now you can see my workshop here in all of its glory. So now this camera can't connect to anything. So let's make some rules on what the camera can connect to and what we can do to connect to the camera. So that might sound great in theory. We can force all of our traffic up to the firewall to be filtered and back. But what about the physical layer implications of this? So layer 2 Ethernet doesn't natively have a way to segment traffic. So we essentially need separate cables and separate switches to carry each subnet. So in this example here, I have the yellow network and the pink network. They each have a switch, they each have their devices, they each have their subnet. So now everything's completely isolated. When a client on the yellow network wants to talk to the pink network, goes up to the router does firewall routing, sends it back. The router then needs to have enough ports for all of these networks we're creating, and we need to have enough cables to do that, and we need to have network switches to do that. If you're in a small building where you run everything back to one closet, that's probably a perfectly adequate solution. And for security cameras like this, I'd argue that separate cabling is pretty much a good idea anyway for security cameras. But for anything else, you don't want to be creating a separate cable for every single TV, IoT device, all that kind of stuff. You don't want to be trunking all of that back with large bundles of cables to your giant mess of switches. But conceptually, designing your network like this, having the segmentation between networks, and thinking of it as separate wiring will lead us directly into VLANs. So herein lies the problem. From the perspective of Internet Protocol at layer 3, it would like separate hardware to run separate networks on layer 2, Ethernet. So layer 2, Ethernet, needs to provide separate tunnels to encapsulate these different layer 2 virtual LANs, or VLANs. So now what I've done is I've bought a nicer switch here. This is a managed switch or a smart switch. So it's a VLAN aware. And remember, VLANs are a layer 2 technology on Ethernet. Layer 3, Internet Protocol, they're subnets. So in this case, from the perspective of the router, its address is 2001 db81/64 on VLAN ID 8. So from the router's perspective, VLAN ID 8 is like a separate port. And on that port, we've assigned it an address and a subnet. Similar for VLAN 9, we have VLAN ID 9, separate port. On the switch, we define this as a trunk port. Now, different manufacturers use different terminology for this. The kind of industry standard is a trunk port, or a port that carries all VLAN traffic. Usually you'd use that kind of port to go between your router and your switch. A lot of times your hypervisor too, for virtualization, will also support trunk ports. So Proxmox can do that. I have a video on VLANs, bridges, and bonds up here. So Proxmox would be on a trunk port, router would be on a trunk port. Wireless access points, if you're doing segmentation that way, can also be on trunk ports. But essentially a trunk port means that the VLAN tagging is enabled. So whatever device is connected to the trunk port needs to be VLAN aware, or it's going to get all sorts messed up. So then the switch internally has a yellow section and a pink section. So that's VLAN ID 8 and VLAN ID 9. And it doesn't care what traffic flows over it, whether that's IP, IPv6, MPLS, something completely different. It's treating each VLAN ID essentially as a separate switch within the switch, with its own switching table, its own MAC forwarding, and it's keeping them isolated by VLAN ID. So in this case, this port's a trunk port, so it's a member of VLAN 9 and VLAN 8. These ports are given what's called a port VLAN ID. And that means that when a packet comes into or out of the port on the switch, it either adds or strips the tag. So for traffic on this port, this is yellow port VLAN 8, when traffic is destined to VLAN 8, it'll be a member of whatever port this is, and it'll strip the VLAN header and just send the packet directly out. If a packet comes in with no VLAN header, it adds the VLAN 8 header and treats it as if it came from VLAN 8. So VLANs are essentially a way for us to use a single switch and a single cable to emulate having multiple switches and multiple cables. Of course, we're still sharing the bandwidth over all of these links. We still only get gigabit on gigabit Ethernet, no matter how many VLANs we add to it. But we get physical layer segmentation as if we had separate cables and separate switches, as long as all of the devices that are on trunk ports are aware of VLANs and they don't mess it up. So now we can have a much simpler network. We can connect more than one of these switches together. We can have a second switch down here. We can connect that with a trunk link. We can have stuff spanning out all over. And all of our traffic on purple, pink, still has to go back to the firewall. All of our traffic on yellow still has to go back to the firewall to get to pink, etc. We've created a virtual implementation of our large physical network we had in the last diagram. So essentially, we took the diagram we had before where we had separate switches and separate cables, and we shrunk it down so we can share cables and we can share switches. But traffic still has to go to the router because the router still has to make layer 3 subnet routing decisions. So now that we got this set up working with a physical port, let's see if we can migrate this over to use VLANs instead. So for the purpose of this video, I'm using a MikroTik Hex as my VLAN aware switch. It's perfectly capable of doing layer 2. This is not a MikroTik config video, so I'm just going to gloss over a bit on how I configured VLANs on this. But basically, port 1 is going to be my trunk port to the router. Port 2 is going to connect to the untagged VLAN, which is LAN, and we're going to make port 3 our camera. So just in case you're curious, this is the MikroTik side. So I have a bridge with all the interfaces. So port 3 here that's connected to my camera has a port VLAN ID of 6. The rest are all on 1. And then over on VLANs, everyone has access to VLAN 1 except for port 3. And port 3 and port 1 both have access to VLAN 6. So over here in OPNsense, we already have physical interfaces, so we need to create a virtual interface for this VLAN tag. Let's go here to Other Types and VLAN. So there are no VLANs yet, so let's create one. So our parent interface, the parent interface is the physical interface on the box that hosts this particular VLAN. So in this case, IGC 0, that's also hosting LAN, and VLAN tag is going to be 6, and this is going to be camera VLAN. So there we go. So now we created a new interface, VLAN tag 6, off of an existing parent interface. So now we need to move our subnet setup from the existing interface to the VLAN. So to do that, we go over to Assignments. And so previously we're using IGC2, which is the third physical port. We're going to switch that over to use parent IGC0 tag 6. And that's it. All the config we already did earlier for the subnet carries over to the VLAN interface, because in reality the VLAN interface is just another interface for OPNsense to use to carry IP traffic. So now that the interface is up, we see it got an address. It's already had the IPv4, got IPv6 just as usual. Go down to Services, and let's see. The camera didn't find us yet, so rebooted the camera so it would search for a DHCP address again. It showed up here, same address as before. And again, logged into the camera through VLANs this time. So for those of you that haven't already jumped to setting up your subnets and VLANs based on what I already told you, now's a good time to think about numbering. How are you going to number your subnets and VLANs? So in the example diagram here, I used some example numbers. So I used VLAN 8, VLAN 9, 2001 DB8, 2001 DB9. Some of these numbers are reserved for documentation, like 2001 DB8. In my other example, I used VLAN 6. For IPv4, I used 10.212.46 and 47. Where did those numbers come from, and how do we come up with our own numbers for our own networks? So the three types of numbers we have to figure out are, what are our IP addresses, v4 and v6, and what are our VLAN tag numbers? So IP addresses are 32 bits long, and they're written as 4 8-bit octets in decimal. That's where you get the 192.168.1.1. Each of those numbers can go from 0 to 255. Some of those values have special meanings. Next up, we have v6 addresses. So v6 addresses are 128 bits long, and they're separated into 8 chunks, each of which contains 4 4-bit nibbles in hexadecimal. Each chunk is separated by a colon, and may have leading zeros removed. If there's a big long list of zeros, we can use a double colon to remove the whole list. But we can only do that once because otherwise it'd be ambiguous. And last up we have VLAN tags. So VLAN tags are a 12-bit number in decimal. So valid numbers for a 12-bit number would be 0 to 4095. But the first and last number are reserved for special purposes. So we can have up to 4094 VLANs starting at 1. So 1 is the first VLAN, 4094 is the last. Those are in decimal. So first off, we're going to start off with IPv6 addresses because they're the easiest. So you'll get a prefix delegation from your ISP that's so many bits long. Business connections are usually 48. Home connections could be 56 or 60. Those are both pretty common. In any case, those are aligned on a 4-bit boundary, so we have a whole nibble to ourselves. So for a business connection, we get 4 nibbles, so that's 4 hexadecimal digits, maximum value of FFFF. For a residential, we'd either get 2 or 1, maximum value of FF or just 1F. But in any case, we have a whole digit to ourselves in the number, and we can play with that how we want. So what I recommend doing is coming up with some sort of addressing strategy where you're using these 1, 2, or 4 nibbles to identify things about the network. So for home networks, you're virtually always going to have one single router. So the only thing you have below the router is the subnet ID or the VLAN tag. So just take that VLAN tag and stick it straight in the address. If you get a /60, you can put VLAN tags 1 through 9 directly in the address. 0 is a reserved VLAN tag, so you can just not use it if you want. You could also use it for untagged traffic for management. You could also use A through F if you wanted and convert them from hex into decimal, or just not use those. If you actually need more than 9 VLAN tags, those are things you have to think about. If you're a residential connection getting a /56, you can go up to 99, so do 1 through 99 with a 01 through 99. And you don't even have to worry about the hexadecimal part. That's probably plenty of VLANs for you. If you're a business, you might have multi-layer routers. So you might have like third floor north, IDF, which has a managed switch doing routing, and then you'll have like all the clients in the third floor north on that subnet. Maybe you're doing that just with VLANs, or maybe you're doing that with layer 3. If you're doing that with layer 3, you could use the first nibble to identify the wiring closet, or the first 2 if you want. So you could have like 2 nibbles for wiring closet 3.1 would be like third floor north. Last 2 the VLAN ID off of that wiring closet. Or you could just type all of the VLAN IDs into your subnet straight out. Ignoring hexadecimal, you can fit the entire VLAN space in the 4 nibbles, which is perfectly fine to do. Don't worry about wasting space. Don't worry about leaving space for extra subnets. Subnets are 64 bits long, so you're never going to run out of space in a single subnet. And yeah, it's pretty simple. So next up, IPv4. In IPv6, we had this nice quirk that every single digit represents exactly 4 bits. So we can subnet mask on that. So we could have like a /56, break that down into 60, break that down into 64. With IPv4, we don't have nearly as many opportunities for that. So each digit is part of a decimal digit. So if you use, say, 99, that doesn't necessarily correspond with specific bit patterns. So if you want to pull out a smaller subnet, it's very hard to do that. So essentially the only numbers we have available to us are the whole numbers in the middle. And those are also pretty reserved because we don't have that many segments we can use. So we could use 10, which gives us 3 different 8-bit decimal numbers to work with. We use 172.16, which gives us like 2 3/4. And we use 192.168, which gives us 2. If you're really, really desperate, you can use 10.64, the CGNAT prefix, but you shouldn't. There's also a couple other random prefixes that you also shouldn't use. So anyway, my recommendation is if you have multiple subnets, to generate a random number in the 10 space and use the second digit as your VLAN ID. So in this case, I use 10.212. If I only had a couple VLANs, I could just use .40 something, so I could have 41, 42, 43, 44 for my VLANs. That would be good. The more randomness you can introduce in this, the better, because if you're connecting over VPNs to other networks, the chance of having a collision is reduced if you use random numbers. If you use 10.0.0, the chance of you connecting to someone else's network that also used 10.0.0 is much higher. So that takes us right into the VLAN tag numbers. So as I said earlier, they can be from 1 to 4094. And if you followed my guide this far, you already know what they should be. You're going to use the numbers from your subnets. If you don't use the numbers from your subnets, you're going to have to figure out what correlates subnet 1 or subnet 47 or something to VLAN 6. How do you know? Just use the same numbering all the way across. It'll be easier. Part of your numbering plan. Another concern with IPv4 is having more than 253 devices on one subnet. If you get to the point that you have more than 253 devices on one subnet, Almost always, it's time for a new subnet because your broadcast domain gets bigger and bigger. And when you have that many devices, you get a lot of broadcast traffic, MDNS, and especially if you're bridging this to Wi-Fi, it's really going to wreck your Wi-Fi airtime. Now that doesn't mean you can't have a /20 or a /18 or even a /16. If you're doing a /16, you're probably doing it wrong. If you're operating a larger scale network, being that wasteful can be a really big problem. A lot of large companies have already run out of space in the 10 region. Some of them moved on to 11, which belongs to the Department of Defense. Some of them moved on from there to 12, which belongs to other people. So those are the kind of things you really don't want to happen if you're planning big networks. With IPv6, though, you don't really have to worry about it too much. The address space is practically infinite. Just don't be really dumb about how you use it. So one last question that comes up all the time in regards to IPv6 addressing is, why don't we just use a private region like we had in IPv4 and NAT that out to the world? Or, I have a special use case. Can I use a private region in v6? And those are two different questions. The first question is, why don't we NAT out to the world? It's because IPv6 does not want to use NAT. We would like to maintain end-to-end connectivity where any node can directly address any other node. The end. That said, properly implemented network prefix translation is a thing, and it is used in multi-homed networks. Essentially, the last 64 bits stay the same, the first 64 bits get swapped out, there's no state tracking, there's no NAT punching. It's a strict one-to-one translation of the first 64 bits. That will be used if you have two ISPs. Your failover ISP would get prefix translated to the prefix from your primary ISP, so clients can still appear to work. That does break some things because clients don't know their own address, but it's less bad than doing NAT. Now the second part of this is, what if I do have a truly private network that truly does not have internet access? How do I address it then? I could just take another subnet from my global plan and use it, but do I really need to? Is there a private space for this purpose? And there is. It's called the ULA space, unique local address. We have a region called FC00/7, which is effectively FD00/8, because the first bit identifies if it's been assigned by a global entity and no global entities assign them. So FD00/8. Now you don't just go doing FD00::1. You're supposed to generate the next 40 bits randomly. So you end up with a 48-bit prefix to use. And you're not supposed to use sequential ones. You're supposed to randomly generate one each time. And the point of this is, if two companies were to merge, two networks were to merge, something has to get cross-connected. Somebody using FD00::1 doesn't cause problems for everyone else. So if you would like to use ULA addressing, there are some really valid purposes for this. And essentially, a ULA address should not be expected to ever speak to the internet. Even if you use NAT or network prefix translation to get this address to the internet, the clients won't do it. So there's essentially an order of address precedence when it comes to choosing an address and choosing a protocol family. So in IPv6, this is very well defined. The highest priority for a client is to use IPv6. That said, there are some more specific prefixes that have lower priority. The second most important thing for a client is to use IPv4. So if it can't get IPv6, use IPv4. Makes sense. But then there are some sub-prefixes within IPv6 that have even lower priority than that. So some of the old transition technologies like 6-bone, Teredo tunneling, those kinds of things are prefixed lower than IPv4. So if a client has access to Teredo and IPv4, it's going to prefer IPv4 because it's not a global IPv6 address. And ULAs are in that same bucket. They're prioritized lower than IPv4. So if you give your clients IPv6 via ULA and IPv4, they're going to send all of their traffic over IPv4. If you give them a GUA, they'll suddenly prefer their global address over v6 because it's higher priority. So where do you realistically use ULAs? I only use ULAs on my backend storage networks. So these are networks that are not connected to anything except the storage servers, or essentially the SAN networks. So I've got my storage nodes, my Proxmox nodes. They've got a private switch. It's not even a VLAN switch, it's just a high-speed private switch. And they're all connected to it, and they use a ULA. There's also some benefit in using ULAs for your management network. That would mean that you have to give the nodes like a proxy for them to get firmware updates and things like that. But using it for management plane networks that aren't supposed to be talking to the internet is also a perfectly valid use case. So there's some websites online. You just load up the website, it generates you a ULA. You can use that for your whole company, your whole site, your whole home, whatever you want. You can keep clicking the regenerate button over and over and over and over until you get an address that you like. Maybe it's easy to remember, maybe it's got some of your favorite numbers in it, whatever. Doesn't matter, it's randomly generated. Use that on your networks. So if you're interested in more discussions on OPNsense, feel free to join my Discord server, link down below. This topic was actually suggested by my Discord community. When I was starting on OPNsense tutorials, I made an emoji poll. And you can kind of see what they wanted to see over here. So the mango won out with what settings you need for functional v4, v6 upstream. So I did that in the first video. Next up was the watermelon, basics of multiple subnets, VLANs, and routing between them. And that was this video. I also touched on the pineapple a little bit, DNS resolve and forwarding, in the past video, but I'm sure I'll come back to it with some more in-depth topics in the future. And that means next up is the avocado, analytics and traffic monitoring. So I'm definitely excited for that video. I haven't started it yet, so if you have any questions about analytics and traffic monitoring in OPNsense, feel free to ask. Comments down below or on my Discord. If you want to support me financially, I have a Ko-fi link down below. Any donations are greatly appreciated. All of the images and diagrams from this are available on my website, link down below. And as always, I'll see you guys on the next adventure.